Okay, now the introduction. We have learned about that the polymers have existed in natural form since life began, and then there are some history that I also give you the video if you watch the video, and I think you need to watch the video to understand how important the foundation of the polymers that is, I think, found by this man Goodyear, these two brothers. They found how that the rubber can be further improved. Okay? So that is how you can have, like, if you see any rubber, usually the color is black, and sometimes it is used for like to cover something, like maybe sometimes in your shoes, maybe like a shoes for like a, how to say that, like a boot, that is made from like a vulcanized rubber. Usually people who works in mining, they go to the mining, and I think they wear like this kind of polymers, okay, this rubber, the vulcanized rubber. And how this man found is actually when he stretched the rubber, like this stretch, like never-ending stretch, right? Like this, you can elongate the rubber really, really long. Okay? And it's found out that the chain molecules, right? The chain molecules is actually, like, you have to know. I haven't prepared in this slide. Let me just draw here. It's really long, but it's like it's layer by layer, not layer by layer. Yeah, you can say layer by layer, but it's not having any connectivity between the layers. So this is empty space. So that's why when you stretch rubbers, you can see that, like, this one, for example, stretched to here, and this one is maybe going there, right? And then that's why it's becoming like really elongated, really stretched out, right? And then how the vulcanized rubber is actually they connect this, right? If you watch this video, they mentioned that he found out that it can be connected through, I think, sulfur, right? And it's because also because of the accident. The inventor accidentally put sulfuric acid, and then it's actually reacted with the rubber and make it more harder, and it can help us to like it can be utilized as many tools, like, for example, like covering something, like in many equipment, like in equipment, especially in industry that needs to have a good materials that lightweight, and it can cover their body. So that's vulcanized rubber. And then also the characters here, he also prepared something that is remarkable even until now, although he died by suicide. And also bakelite. So those are just history part of the polymer. This is the man, okay, Bakelin, Staudinger, and characters. And then we already have until here and also here. So this is a polymer by definitions. Okay? It's a large molecules, long sequence. It has more than one species of atoms or group of atoms, and they are linked together by primary bonds, usually covalent bond, and most is covalent. I think all is covalent. We can say all. And terms macromolecules, it's formed by, they are linked together, the monomer molecules, the unit that repeated, okay, through chemical reaction. And we call that reaction as a polymerization. Okay? Okay, so this is something that I need to add and need to mention because this is a very basic root for a polymer. So if we look here, this is what we call a paraffin compounds. So like CH4, C2H6, methane, ethane, propane, butane, and hope you still remember how to take the name, how to make the name of all of this, and if this double bond, how to make it into different name, even, right, and so on and so forth. But this course is not only like to remember those names, but just to let you know that we are going to have that kind of terms in the future. Okay. So polymers start with the hydrocarbon molecules because this is the basic atoms or basic compounds that is going to be polymerized, okay? That we are going to see in many polymers. And all polymers, they should have this C backbone, okay? The chain structure backbone. So the primary structure should be having this carbon, okay? And then we need to also referring to some functional groups, okay? Functional groups. I think this is pretty common, and I think you already learned also in chemistry, like the alcohols group, the ethers, carboxylic acids or acids, aldehydes, and then aromatic carbons. This is to make sure that this is having each of the corner having the carbon also, right? It's just to simplify the aromatic structures. This is how the name usually, right? Okay. I think that's okay. And because the functional groups is the one that we are looking for when we polymerize something. Okay. So when we polymerize, so when you want to make a monomer connected to other monomer, you need to think on what kind of functional groups they have. Okay. What kind of functional group they have. So let me write here. This is important for polymerization. Okay. So important for polymerization or reactions or synthesis, okay? Polymer synthesis. Okay, and then this is what example that might be in a very simple. We call this is an addition reactions or addition of monomer. We will learn more details about that later, but what I want to just introduce here is from this monomer, okay, this is the ethylene. We are going to react this ethylene, okay, with this. Usually if you see something with one dot like this, we call this unpaired electron, right? Unpaired electron. So let me write here. I think we can make it a little bit here. I think make it a little bit thick. Okay, so unpaired electron. Okay, what does this unpaired electron doing here when we add with the monomer that we want to react? So usually, how we can get this unpaired electron? Usually we need some catalyst, or we usually call it initiator. So let me write also it is an initiator. So let me write here an initiator. Okay, so based on the name itself, initiator. So it is to initiate something. So it needs to trigger something. Okay, what's something? That's the reactions, of course. Okay. Okay, so usually it has the unpaired electron because this unpaired electron, they want to look for their friends, right? So if you remember in chemistry, I think in chemistry, I think you already learned, the electron, they need to be paired, right? So that they are connected, right? So if this only having like one single electron here, this single electron doesn't want to be single. He wants to be mingled, right? He want to find a partner, right? He want to find a partner. And how does this electron find a partner? You see, in this polyethylene, or in this ethylene, we see this double bond. There is actually, because it has many, right? So this is how I can give you some perspective, or maybe you can have this as your reference also. But I would like to share that this, okay, this one here, it has 4, right? Many, right? Like if you are in a really populated place, like it's too much people. Maybe some people want to migrate, right? They want to look for another place. And this is like, this single electron is like, come to me. And then it's broken this bond. Okay? It's broken this bond. So that's why this, and because it's broken, then this carbon can pair with this, okay, as we see in the result here. Okay. And of course, there should be a consequences, right? The consequences is when does this the chain broken, the single pair is transferred to here, okay? Okay. Okay. And then what's happened? Is it over? I think no. Another single electron, right? Another one. So let me write here another unpaired electron. Okay. So this unpaired electron, again, the electron looking for a friend. Okay. And in a process of polymerizations, the monomer is not a single monomer, right? It has many monomers. So the unpaired electron also looking for other ethylene, other double bond, and they found one. Okay, and then it keeps adding, and that's why the name is addition. Addition polymerizations. So it's formed by sequential addition of monomer units. Okay. And then because a lot of ethylenes combined becomes one, okay. So add one, and it becomes many, and the chain becomes really long. And sometimes we write this the monomer, and then it's just to show that it has many repeated units. That this is the repeated units. Okay, and then it goes the same way. So another unpaired. This is also unpaired electron, and it's broken this chain. The double bond is broken, and then connected, and then the single electron transferred to the end, and it goes all the time. Right? And how does it end? We need to terminate the reactions. There will be a terminate, but I think we will discuss later. Okay, but this is to show you the one of the simple polymerizations, okay? And we call it the addition. The addition. So usually we write, can write this, or it's simply like CH2, and then N. This is polyethylene. Okay. Okay, we are going to see more later when we learn on the chapter on polymer synthesis or polymerization, because this is just to show you that just a brief intro what kind of reaction that we will have. Okay. And this is just a one method. And there are at least 3 methods to learn. And if we look on how the structure, if we look on if we just write in a paper, we could just write like that, repeating it. But if we want to see the real structure, how does it goes, what kind of molecules, it's actually like this. It has a zigzag structure. So it has a zigzag backbone structure. So this is the C. And this is H. And this is also something that we might also learn, I think, in the structure, or maybe later in the second part of introduction, and maybe I will show you again. So because we have the isomerism, right? The isomerism, like how does it, how the pattern of the polymer can be, or tacticity. Okay. This is the structure. And then there are other examples as well that took similar reactions like the previous one. So we could have this with F, with the fluoro. We could have with the chlorine. And of course, from this example, we could conclude that we could have this with some other R. So R can be any functional groups that can be adjusted. Okay, can be adjusted. So the similar reactions, basically right here. Similar reaction process with this. Okay, and then some common polymers. So the one that we discussed before, polyethylene. If you change one hydrogen with chlorine, it's become the polyphenol chloride, PVC. If we change to the fluoro, all the hydrogen becomes the PTFE, polytetrafluoroethylene. And if you change the one hydrogen, it becomes this CH3, it's become polypropylene. So it's all the common polymer that we have in our daily life, actually. So you can find, I think you can find polypropylene in your bottle, right? You can see if you check the name, usually like PP, that is polypropylene. And the polystyrene, of course, it's like in your styrofoam and others that has that structure. We have also the polymetal methacrylate, the bakelite, the phenylformaldehyde, the nylon, okay? The nylon, of course, in your clothes, polyester, PET, polycarbonate, like maybe like a fiberglass, something like that, that is transparent, okay? Okay, that's just a common polymer. I think we will discuss some of them, okay? And then we move on to more on the a little bit structure, how to define them, how to distinguish them. Okay, first is based on the structure we call the skeletal structure. So I think we learned here this one, right, last time. Linear, cyclic, and if it's branch, we could have this kind of branch, and we can have many branches as well. We can adjust them, okay, as long as we know like what kind of functional groups that we would like to have. Okay. And then the network, it's actually 3 dimensions, but it can have connected to every direction. Sometimes we call this directly the crosslink, crosslink polymer. You could also say a crosslink polymer. Okay. Right here, another terminology, and I think some textbook they also use the crosslink polymers. So they are the same thing. Okay, the network, crosslink polymers, same thing. Skeletal structure. Let me check. Okay. Okay. Another skeletal structure is we call the dendrimer. This is a highly branched polymer that is well defined. Okay, well defined. The structure has a pattern. Okay. Like in terms of geometry, the pattern is well defined. And this hyper branched polymer, this is a random defined. Okay. They're similar to dendrimers, but it's not that well defined. Okay, now after we know the skeletal structure, the other things that we are going to see is a homopolymers. This is just to note that this is the polymer that derived from one species of monomer. So they will have, like, for example, the A is the same like before, like the polyethylene. Okay? So this also we call the homopolymer. Okay? So this is A. A is the repeat unit. Okay? Right here, A is the repeat unit. A is the repeat unit. Okay. Now we could just write those A, and then we have a bracket and just N, okay, which denotes that this has many A linked together, right? Okay. Okay, that is homopolymers. Some example here. I think similar example with before. Okay. We consider the table also as a homopolymers. You can see some comments for each polymer. For example, the ethylene. Okay, it's for film, for a molded object, for tubing, like a hollow tube, for the insulations. Okay, so insulations, I think for cables as well, and polypropylene. Okay, it's more stiffer. That's why it's useful for like a plastic bottles. And tetrafluoroethylene, the PTFE, it's for coatings, for cooking, right? Teflon. Because it has low friction. Okay, so that's good for cooking, because cooking they need to have a lot of frictions between the pan and the spatula, right? And styrene, for molded object also, and it can improve rubbers also. The PMMA, for moldings, for aeroplane window. Yeah, I remember. Yeah, aeroplane windows. This is other, I think, commercial name, plexiglass and so on and so forth. Vinyl chloride for piping usually. I think you can see a lot, okay, in piping. in housing, piping and housing. Okay, and then the phenyl acetate, PVA for coatings, for surface coatings, for adhesives, for gum. Okay, yeah, PVA, a lot of them use as coatings. The polyethylene oxide for packaging. Okay, for packaging. Ethylene glycols. This is some of them for. So it has two. Okay? So ethylene glycol and terephthalic acid. Okay? So they are two, but still considered as a homopolymer because they both are repeated. Okay? We will see what the difference with the homo and then the other one is we call the copolymers. Okay? So we still consider this as two monomer units, okay, but it's considered as homopolymers. And then the polyhexamethylene sebacamide or nylon. Okay, nylon has a variations. Okay, we call this a nylon 610. Okay? Nylon 610 because it has a 6 carbon here and 10 carbon here. Okay? This is different structure. So this structure here with N and N, it's 6 carbon here, so we call it 6 carbon. And C and C here, and 8 carbon in the middle. So 8 plus 2 becomes 10. So it's called N 6 and 10. Okay? The other common nylon is 6, 6. Okay? 6 and 610. Okay, so the difference is on the carbon. Okay, so it has a two monomer. Okay, so this is the first monomer. This is the second monomer. And of course, nylon is for fiber, right? Fiber. Okay. Now, the other things is copolymers. Okay, so we have the homopolymers, that is one species or more, but it's make a group. Okay, make a group. And the question, how to differentiate with a homopolymer? So we are going to see the structure. Okay, the structure. So if the structure is making a monomer, or maybe two monomers, like one monomer, then we consider that a homopolymer, like the previous one in the table. Okay? But here, this will be different. Okay? It says that describing polymer whose molecule contains two or more different types of repeat units. Okay? So we are going to see what structure the copolymer has. Okay, what's the difference between the homo and the copolymer? Okay. Sometimes copolymer also determined by the how many repeating units. Like if it is like having 3 different repeating units, maybe or maybe more, or maybe if 3, it's maybe third polymer, or maybe bipolymer, but it's not really that common. But we can say that also. So the copolymers, it can be adjusted, okay, like this. You can say this two, the statistical and the random, is like a similar, but random is more like if A and B are 2 different repeated units. Let me write here. A and B, let me write here, maybe A and B are two different repeated units. Okay, so that's why it's different from the nylon that we discussed. So nylon we can consider as a homopolymer because it's repeated all the time, the same. Okay, but here the two different unit, we could say it's practically random. Okay, practically random. But sometimes the random one will make some distribution. If it's based on the statistic law, we call it statistical copolymer. Okay? But if still we don't know why the distribution is different all the time, then we call random copolymer. Okay? And then we could also say we have the alternating copolymer. Okay? A, B, A, B, A, B. Okay. And then usually if we know how the polymer's structure is, how the repeat units behave, we could write like in a, usually write with the statistical random, okay, or alternating copolymer. Okay? Later I will show you. But we have here first we call the block copolymers and graph copolymers. Okay? So the difference between these two is if you look at the branches, if you look at the structure, and I write here in the first paragraph why this block and graph is important, okay? Especially if you are going to do some synthesis in the future. If we look back, the random copolymers, they are naturally they are not really in a good property, okay, for average in compare with the homopolymers. Okay. Yeah, well, you can imagine, okay, if the homopolymers they contribute with single property. So for example, you have a homopolymer like that. Well, maybe let's say it has good property for maybe just take some stronger than most polymer. And you have maybe B. That may be considered not as stronger as A. If you combine these two, like maybe B, and randomly, maybe that polymer is not as strong with the homopolymer A, right? If we combine. So that's why we need to have something else. How can we combine these two without reducing the A property? And maybe we can improve B. Okay? So maybe B weak but maybe good isolate. So maybe weak but good insulation probably. So how do we make polymer that is strong and then it has a good insulation property? So if we want to combine A and B, we need to think something. We cannot like blend, just like blindly blending these two. If we blend these two together, well, it will probably become just a random copolymer. I'm still not sure what kind of polymer, like I just saying it is A and B just for illustration. But this case is the property might be changed, right? So that's why this block and graph is important to at least to improve. Okay, to improve. So first we call the block copolymers. Block. We have the first one is A and then B. The second one is A and then B and then A. Okay. So it's a linear copolymers, and the repeat units exist along the chain. Okay, along the chain. So we call that a block copolymers. And then graph. So it is a branch polymers. So the difference is this main structure is one single monomer, while the branch is another one. Okay. So it's like A, and then the branch is B. Okay. So perhaps this is a good choice if we could graph B onto A and make it strong but has a good insulation. Okay. So we could have a graph copolymers. So it is possible to combine the property of some homopolymers into one single material. Okay. Okay, this is how we name it. Okay. So we usually name with poly A if we not sure like what type the polymer is. We just use the it's copolymers, A, COB. Or we know if this is statistical, we write stat, random, ran, alternating, ALT. And if it's a block, we write block. And if it's graph, we write graph. Okay, and this is example for the simplification for the main chain is A, the branch is B. Okay? Because sometimes the grafting can have many branches. Like not only B, maybe C, D, and we can arrange. So if it's not simplified, then there will be like a lot of variations. And if you see the chemical company, if you buy some chemicals, they provide this usually. If you like to buy some polymer that need to be synthesized, so usually they also use this block and graph as a like you can think like a model kit, like you need to assemble it, right? If you buy toys like need to be assembled, this is like toys. So if you buy like a chemical or a polymer, you buy, and then the company they provide already in block and graph, and they already prepare fractional groups that easily to be react. So that's why they have different kind of, even though maybe the main linear chain is the same, but maybe the branch different. Depends on what we want. Okay? If we want to combine with other chemical property, then we need to look for what kind of reaction we need to have. So they provide this data. So we know, oh, this is a block copolymer, oh, this is the graph. Okay, but I think I need to end until here, okay? Because I think it's already 9 minus 2. So we will go by this classification of polymers. Okay? So still introductions, and we are going to see that the polymers can be differentiated by at least 3 thermoplastics, elastomers, thermostats. Elastomer is what you call rubber, okay? Is what you call rubber. And thermoplastics is what we call, like in daily life, plastic. It's actually a thermoplastic. Thermosets, if you're familiar with resin, if you know resin, you play with resin before, like usually if you want to build some, how to say that, they usually you give certificate and some placate or some like if someone won award, usually it's made of some of it made of resin. I could say some of the examples of resin. And we are going to learn more about this in the next Monday class. And as I said before, maybe in the next week or next 2 weeks, we are going to have a discussion group for the Thursday class. So not every Thursday you need to come. I will announce like when this will happen. And after that time, you need to have like a summary and maybe some results. I will give you descriptions later. So you don't need to come every Thursday. So I will announce in a moment. Okay? I will announce in a moment.